All right, well, it is 1 o'clock, so we will get things rolling then. Hello, everybody. Thank you for sticking around for my session, and thank you for Julie for that great lead-in, giving a nice overview of the optimization capabilities added in FreeFlyer 7.6. My name is Quinn Kupek. I'm a member of the FreeFlyer technical support team, and I'm going to be going over a mission plan I created using FreeFlyer for optimizing Earth-Mars transfer trajectories. So first up, just a little bit of an introduction, or just our quick agenda. I'm going to do an introduction, give an overview of the mission plan. Then we'll go through the first optimization sequence in the mission plan, and there are 3 elements to that: the setup, the evaluation loop, and then our visualization/results. Then we'll do the second optimization sequence, which has those same 3 components. And then we'll look at an analysis of the solution that I came up with, and finally, I'll field some questions. Just as a reminder, everybody is muted, and we're gonna keep all participants muted. So if you have any questions, please put them in the chat, and Mark will ask them to me at the end of my presentation. So first, let's do just a brief introduction here. So we want to solve an optimal Earth-Mars transfer based just solely on minimum delta V. We're not considering any time of flight constraints or time of flight optimization. We're also going to use the 2020-2021 transfer window. This is the same transfer window that the Mars Perseverance rover, as well as several of the other Mars missions that launched this past summer, are using. And we're going to start in a circular low Earth orbit and end up in a circular low Mars orbit. Finally, we're basing some of this on some preliminary analysis that shows that our delta V should be approximately in the range of 4 to 9 kilometers per second. I pulled this handy little graphic off the NASA Ames Research Center trajectory browser, which shows the highest delta V there towards the end of the transfer window at 9 kilometers per second, and then the lowest delta V in blue at the beginning of the transfer window down towards 4 kilometers per second. So this is going to serve as just a nice little sanity check for us as we go through our mission plan. Next up, I want to talk a little bit about Earth-Mars transfers. Traditionally, if you want to solve an Earth-Mars transfer, you're going to use a Lambert solver. It's really nice for some quick and dirty analysis. It gives you, pretty easy results, nothing too bad like that. But unfortunately, you make a lot of assumptions when you do that. So you're usually assuming two-body dynamics, and frequently you're ignoring patched conics. I have seen some Lambert solvers that did consider patched conics, but that's not usually the norm. The other thing is, a Lambert solver is great if you have departure and arrival dates, and it'll give you the delta V for those dates. But if you want to find a minimum delta V, you're going to have to set up a parametric study to consider varying arrival and departure dates and find out the minimum. And that's how you get into pork chop plots. And having done that several times, can say it's not the most pleasant thing in the world to do. So, Lambert solvers, okay for some analysis, but not ideal for everything. That said, I ran the Lambert transfer calculation sample mission plan that's delivered with FreeFlyer. And this I put in the departure and arrival dates that we're going to use here. That gave us a delta V of approximately 6.4 kilometers per second. So that's going to serve as our baseline that ideally we want to do better than using optimization. The final thing that I want to talk about in my introduction is just an overview of some of the optimization terms I'm going to be talking about. I know Julie gave a really nice comprehensive optimization overview, so I'm not going to get into the details of that too much, but just a couple quick little reminders. First off, constraints. Those are requirements that the optimizer must satisfy. Next up, state variables, aka free variables. These are things that the optimizer can change to achieve its goal. Our objective function, which is going to define the goal that the optimizer is trying to minimize or maximize. In our case, as I mentioned, we're trying to minimize total delta V. And the final thing I want to talk about that wasn't covered by Julie, because it's more of a complex topic, is multiple shooting. So multiple shooting is when we represent the trajectory using multiple smaller trajectory segments. And then you constrain these segments to be continuous. So single shooting is sort of the typical optimization approach. You want to go from point A to point B, and you start from point A, and you constrain at point B so that your trajectory gets there. So that's shown on the top here in yellow, your evaluation trajectory, a guess of the optimizer, and then the constraint that's pulling it towards point B, and then your green solution there. Multiple shooting, which is the approach that I used for part of this mission plan, involves departing from point A and departing from point B and trying to meet some point in the middle. So we've constrained in the middle there to line up our trajectory segments. And theoretically, multiple shooting and single shooting should give you the same result, which is why that green solution trajectory looks the same. But in practice, there's some intricate details of single shooting and multiple shooting that makes one approach better to use than the other, depending on the problem you're trying to solve. In this mission plan, I actually use single shooting and multiple shooting. The first optimization sequence is going to use a single shooting approach, and then the second optimization sequence is going to use multiple shooting. So you'll get to see both of those implemented in FreeFlyer. Next up, just a quick overview of the freeforms in this mission plan. I did this all in 8 freeforms. The first 2 are not going to be discussed at all. That's just console and visualization setup, so nothing that interesting there. After that, there are 3 freeforms dedicated to the first optimization process, and then 3 freeforms dedicated to the second optimization process. And we'll go through all of those in detail. Just a little bit about this mission plan. It's based on the optimal Earth-Mars transfer sample mission plan that was delivered with FreeFlyer 7.6. So if you're interested in my talk and you want to look at where I sort of base this off of, you can go take a look at that mission plan. It solves this problem in a little bit less detail. The other thing is we're using 2 optimization processes, like I mentioned. The first one is going to use NLOpt with the augmented Lagrangian algorithm and the SLSQP subsidiary. You can go into the help file and read up more about the different algorithms available with NLOpt. These are actually the default algorithms, and they just gave me some good convergence behavior, so that's what I went with here. Second process uses IPOpt. Again, I just got better convergence behavior using IPOpt. There's some sort of guess and check that goes on behind the scenes there when you're picking an optimization engine to use. Some other details, we're using a departure range of July to September 2020. We know ideally our minimum delta V should be around that point, and then our arrival range is from February to April of 2021. And once again, we know our minimum delta V should be roughly in that range. One last note, our spacecraft are going to be propagated using an RK45 integrator. We didn't quite need the fidelity of an RK89, so the 45 provides a nice compromise of high fidelity propagation while doing it a little bit faster than an RK89. And also Earth, Mars, and Sun are all going to be modeled as point masses, so not considering anything like J2 effects on propagation. As a note, I used variable step sizes for the evaluation loops, but a fixed step size for all of the visualization. And that's just to improve runtime, but still get smooth visuals at the end. So let's start getting into the meat of this here with the first optimization sequence. It's used mostly to find an optimal transfer time, so what exact departure and arrival dates we're going to use. But I did throw in the Earth parking orbit parameters to be considered here as well. We're modeling the escape burn as a VNB impulsive burn, but the arrival burn is actually just going to consider a difference between the spacecraft's velocity and Mars velocity. So no patched conics around Mars, no parking orbit yet. The spacecraft's initial semi-major axis and eccentricity are constrained to a 12,700 kilometer circular orbit around Earth, also known as 2 times the radius of the Earth. Our first optimization process actually was originally a solve rather than a minimize. I know in Julie's presentation, she got into some nice details about using solve versus minimize. Typically, you would think that if you're using an optimizer to feed into a second optimizer, you would want to use a solve since you're just going to re-optimize those constraints. But since there are so many different feasible transfers within the transfer window, the solve was producing one that wasn't actually that close to the minimum solution. And so when we seeded the second optimization process, it was taking it much longer to get to a minimum solution. And so overall, I was able to reduce runtime by using a minimize in this one, as well as a minimize later. And so that just made a little bit more sense here. So here's just a quick diagram of what this is going to look like in FreeFlyer. We have our Earth departure burn, followed by a yellow interplanetary trajectory, and then our red Mars arrival burn. This is going to get a little bit script heavy, so I've tried to color code everything as much as possible. So blue is going to be anything relating to our Earth orbit, yellow will be our interplanetary trajectory, and red will be anything at Mars arrival. And you can see that here. I've made a diagram that's going to follow along with us on all of our slides. So first up, let's talk about the setup for the optimization sequence. So, just one other thing of note here is that while this is already a bit script heavy, I did remove some of the mission plan that wasn't necessarily critical, wasn't as interesting. So things relating to visualization, initializing variables, or just some repeat things like initializing multiple orbital elements. I took those out. So if you copy paste this into FreeFlyer, don't be surprised that it does not work. If you are interested in going into more detail, shoot us an email. And I'd be happy to go over that with you a little more later. But in the interest of not having walls of text, some parts of the mission plan have been removed here. So the first thing that we need to do when we start our setup is initialize our departure epoch. What we're using is a seed halfway between our two epochs of July 1st and September 1st, and we're assigning that to a state variable. And then we're going to assign all the orbital elements, the inclination, right ascension of the ascending node, true anomaly, and argument of periapsis as state variables. And this will be for the Earth departure orbit. As a note here, we're using a range of 0 to 720 for these orbital elements rather than the typical 0 to 360. This is because sometimes the optimizer can get sort of caught up on an edge case, right, around that transition, around the 360 point. So by going 0 to 720, and then we'll normalize this later, it helps keep the optimizer from getting stuck and overall just improves convergence behavior. So the next thing we do in setup is we add in our arrival epoch using the same sort of deal as our departure epoch halfway between our two bounds. This time it's February 1st and April 1st of 2021. And the next thing we need to do is initialize our escape burn. So we're using 4 kilometers per second as our initial guess in the V direction and 0 in the N and B direction. You'll notice we have much higher bounds on the velocity direction rather than normal and binormal. That's because we know that in an optimal case, the burn should primarily be in the normal direction or in the velocity direction rather than normal or binormal. Next thing is we're going to add some constraints to the optimizer. Specifically, we're just using one constraint for this first optimization sequence, and that is our range from target. And we're setting a lower bound of 0 and our upper bound to be 5 times the radius of Mars. The reason this constraint is here is so that FreeFlyer actually solves something, right? Because of course, the minimum delta V scenario for a transfer is just not to transfer. If you use no delta V, that's a minimum. But that's not achieving our objective, so we add this constraint there to make sure that at the end, it does end up arriving at Mars, or at least somewhere pretty close to it. And the thing we're going to do after that is load in our optimization engine. We set our feasibility tolerance to be 1 e to the minus 10. We want a pretty high fidelity solution coming out of this, which is why our feasibility tolerance is so low. And then we load the NLOpt engine. So next up, we're going to talk about evaluation. First thing you want to do in your evaluation loop is save off your object to process. In our case, that's just the interplanetary spacecraft. The next thing you'll notice is we're going to run while the optimizer has not converged. So we're telling it we don't want any solutions that are not an optimal solution. So just keep going until you find an optimal solution and then report that out. At the top of our loop, we restore objects in process and update the state variables. Pretty boilerplate stuff there. And then we initialize the interplanetary spacecraft. So we get a time span from our departure epoch, and then we initialize that as the epoch of the spacecraft. And then we set all of our orbital elements. So this is where that normalization comes into play that I was talking about earlier. We're using the adjust cyclic range function with the bounds minus 180 to 180. And that transforms our 0 to 720, which is not a valid range for orbital elements, into a range that FreeFlyer can handle of minus 180 to 180. Again, helping eliminate those edge cases for the optimizer, just makes convergence behavior better. After that, we're going to configure our escape maneuver. We pull all the state variables and assign them to an array, and then we assign that as the burn direction. Next, we maneuver our spacecraft using the escape burn. And then we're going to step our spacecraft to the arrival, so we get the step epoch as a time span. Now, this is one interesting thing that we did here to improve convergence behavior, is I added this if statement where we checked the spacecraft's energy. We know that if the spacecraft is still around Earth's orbit, then its energy, it's in a bounded orbit, so its energy is going to be less than 0, which is not what we want. We want this to be in a transfer orbit, so we want an unbounded orbit, energy greater than 0. And so if it hasn't escaped Earth, what we're going to do is just cancel out that step epoch and set it to the spacecraft's current epoch so that it doesn't step. This is because we're using a variable step size, and since if the spacecraft remains in orbit around Earth, FreeFlyer is going to use a small step size, which means it'll take much longer to propagate it out to our arrival epoch. And we know that it won't be a valid solution. Any solution that's going to be valid actually has to transfer to Mars. So we just don't want to waste our time stepping. So we just tell FreeFlyer not to bother stepping. That said, after that, we're going to step the spacecraft to the step epoch, which ideally is our arrival epoch, although in some cases, if we have not escaped, it wouldn't step at all here. Next up, we'll do our arrival maneuver. So we just take the difference between the spacecraft's velocity, or between Mars's velocity and the spacecraft's velocity, and assign that to our arrival burn components. Then we update our range from target constraint with how far away the spacecraft is. And we update our objective. Our objective here is just going to be the sum of the normalized components of both the escape burn and the arrival burn. You'll notice we don't actually perform a maneuver command using the arrival burn. That's because we're not propagating the spacecraft anymore once we reach Mars and take that difference. And then finally, we'll call opt.minimize on our interplanetary objective, and that is the end of our evaluation. So we're going to go into our visualization for the first optimization process. Once again, you want to restore the objects in process, and that reverts them back to the state that we saved at the start of the evaluation loop. Then we get our interplanetary epoch and orbital elements. You'll notice that instead of using get state variables, we're now using get best state variable values. This is because, as Julie noted in our presentation, the final iteration is not always the same as the best iteration, and we want to make sure we're using the best values, which is why we do that here. And again, we use the adjust cyclic range function to get the orbital elements in a value that in a range that FreeFlyer can handle. We pull our escape burn once again, and then we perform our escape burn. That's pretty much the same as the evaluation loop, except we're getting the best values rather than just the state variable values. And then we go ahead and we step our spacecraft to the arrival epoch. You'll notice we don't have anything here checking if we've escaped Earth. We know that if it's found an optimal solution, it has to have escaped Earth, and so that if statement isn't needed. And then we're going to update our view window, of course, while we step it there. And once again, no need to actually perform an arrival maneuver, but we still want to get the value so that we can report it out. And that's going to be Mars velocity minus the spacecraft velocity. So here's the results of the first optimization sequence. We depart July 29th, and we arrive February 20th. Our time of flight is 206.5 days. We have a departure delta V of 3.168 kilometers per second and an arrival delta V of 3.209, giving us a total delta V of 6.377 kilometers per second. You'll remember that our Lambert solver used 6.4 kilometers per second of delta V, so all right, we've already beaten it, but we haven't beaten it by a whole lot, and there's still a lot more factors that we need to consider here, like our patch conics. So while we can already see optimization as an improvement, there's still a little more work we can do. And with that, we're going to add a second optimization sequence. The second optimization sequence is going to solve the entire problem, including both parking orbits. For this, we're using our multiple shooting approach that I talked about earlier, and this is primarily to handle the patch conics around Mars. So what we're doing is we're modeling one spacecraft departing from the Earth parking orbit and going into an interplanetary orbit, and then another spacecraft departing the Mars parking orbit and going into an interplanetary orbit to meet the first spacecraft. The main reason that we need this multiple shooting approach here is that a single shooting approach has a hard time with the transition from a hyperbolic orbit to an elliptical orbit. There's just a lot of sensitivity there that we'll talk about a little bit later, and the multiple shooting approach handles that better than a single shooting approach. Our escape burn, still modeled as a 3-component VMB. Our arrival burn is now actually going to be a maneuver, and it considers our parking orbit but it's only a burn in the velocity direction. That's because we know an optimal solution doesn't have any normal or binormal components. Earth parking orbit is unchanged, and our Mars parking orbit that we're using now is 6,792 kilometers in radius in a circular orbit, and that's also at 2 times the radius of Mars. Additionally, we're adding a third burn in here, our mid-course correction burn, which will take place at the patch point where the 2 trajectories meet. The final results are still going to be integrated using just one spacecraft, and that's going to help us validate the solution to make sure that even though we use 2 trajectory segments to solve it, it still integrates cleanly as one segment for the final solution. So what does this look like in FreeFlyer? We have our Earth departure burn again, forward propagated segment, and then our purple thing here is our patch point / mid-course correction burn to join the 2 trajectory segments together. We have our Mars arrival burn at the other end and a back propagated segment highlighted in lime. Once again, these colors are going to carry through in the color coding to help you follow exactly what parts we're talking about. Shown here is a highlight of the Earth departure burn. So we start in a circular orbit and transition to that hyperbolic departure. And then at Mars, once again, we start in a circular orbit and transition to a backward propagated lime segment hyperbolic departure. So you'll notice the diagram's changed a little bit here as we're converging from both sides towards the patch point, and now we have 2 burns to help get us there. So we're going to set up the second optimization sequence. The first thing we're going to do is actually pull the results from the first sequence and store those in a results array. We're going to add in our optimizer, this time called opt2, and then we're going to add the state variables to the optimizer. First off, we're going to initialize our departure epoch. You'll notice that we're using the results from the first process, and we've also tightened up our bounds a little bit here. And that's because we know roughly, we found an optimal solution, so we don't need to consider as much variation about the epochs for this one. And then we do the same thing for our orbital elements: inclination, right ascension of the ascending node, true anomaly, and argument of periapsis. Again, with reduced bounds on all of those. We do the same thing for our arrival epoch and our escape burn, where we pull those from the state variables. You'll notice we're using much tighter bounds now on the escape burn. We're using only ±1 in the velocity direction and ±1/2 kilometer per second in the normal and binormal directions. This because we know that the magnitude of the last escape burn from the first optimization process was approximately 3 kilometers per second. So any variations in the escape burn should be much smaller than that, and there's not really any need to consider the 5 kilometer per second bounds that we had before. As we continue on, we now add some new stuff, which is our patch point epoch. The patch point is initialized at halfway between the departure and the results for the departure and arrival epochs, and we allow that to shift 80 days in either direction. We then add in our arrival orbital elements. You'll notice that for right ascension of the ascending node, true anomaly, and argument of periapsis, we're using the range 0 to 720 again. But for inclination, we have much tighter bounds. We're using only -45 to 45 with initial guess of 23. That's because we know that in an optimal case, we should be coming in that range based on the way Mars is inclined with the plane of the ecliptic. That should be an optimal orbit transfer in that window. So we can restrict the inclination value because we know roughly what it should be. Finally, we add our insertion burn, which we did give pretty high bounds just to allow the optimizer to play around there, even though we know it should be much smaller than that. And once again, as a note, we're only adding the velocity component, not normal or binormal components for that burn. Here we've got some constraints that don't really apply to a specific part of the mission plan, but rather apply to a few different parts. So these are what we call guiding constraints, which is something that I didn't have in the first optimization sequence. But the 3 things we're constraining are the post-escape eccentricity, so the eccentricity after we leave Earth, the post-burn semi-major axis, which is the semi-major axis after we leave Mars, and then an RDV, or radius dotted with velocity constraint. So guiding constraints are constraints that we know are going to be satisfied by an optimal solution. So they don't help necessarily, they don't make an impact on what the solution will be, but they help the optimizer get there faster, right? We know that any optimal solution is going to have hyperbolic transfers leaving from Earth and Mars. So we can eliminate any guesses that the optimizer uses that don't have hyperbolic transfers using these constraints. The RDV constraint is used to constrain periapsis. This ensures that our burn is occurring at the periapsis of its orbit because we know that that is the optimum point to perform the burn. And so we want to help the optimizer realize that as well. The other constraint we're going to add is a constraint block, and that's 3 elements for our patch point, all of which are going to have equality bounds of 0. This will handle the position differences between the 2 spacecraft at our patch point. And obviously we want a bound of 0 because in order for us to integrate this using 1 spacecraft at the end, we need both of our trajectory segments to wind up at exactly the same point in space at the patch point. Finally, we're going to add one more constraint to the optimizer, and this one's also a little bit of an oddity. We add a constraint burn for the 3 components, or we add a constraint block rather, for the 3 components of the mid-course correction burn. This constraint isn't really used to constrain the optimization process, right? We know that our mid-course correction burn is going to be in that range no matter what. This constraint is strictly there for us to get the best values of the mid-course correction burn once we go into our results loop at the end. There's an optimizer.getBest constraint value method that allows us to pull these. And so this constraint's really just there to allow easy retrieval of the values. Finally, we're going to load in our engine. And for this, we're using a feasibility tolerance of 1 e to the minus 6, relaxed a little bit from our first optimization process. You'll note we have a higher maximum nominal evaluation count of 4,000 iterations. And then we load engine 0, also known as IP opt. All right, and then we're going to go into our evaluation. So once again, we save off objects to process. This time we're saving off both the interplanetary spacecraft and the Mars spacecraft. You'll notice we're now using while the optimizer is running, not while the optimizer has not converged. This is because while we get pretty close to an optimal solution, it's not technically what the optimizer would consider an optimal solution. And that's due to a lot of the sensitivity going on here in the mission plan. And we'll discuss that in the analysis of the solution. But as a note, the optimizer runs for 4,000 iterations, but it finds the solution after about 2,000 iterations and doesn't really change after that, which indicates that it's found what is for pretty much all intents and purposes an optimal solution. But if we did use optimizer has not converged, it would throw an error here rather than just exit out once it hits 4,000. And we just want it to exit out and give us the best solution that it's found, which is why I changed this. Next up, we restore our objects, zero out the mid-course correction burn, and update the state variables. We update our interplanetary spacecraft epoch to be the departure epoch. And once again, we use adjust cyclic range to handle the value of the orbital elements. After that, we initialize our escape burn the same way we have before. We assign the burn direction and maneuver the spacecraft using the escape burn. After that, we're going to set the constraint value for our first guiding constraint. So this is the post-escape eccentricity. So after we've performed that escape burn, we're going to check that our spacecraft is in a hyperbolic orbit and assign that value here. We then get the best state variable value for the patch point epoch, and we have that same if statement as before. So we're checking, in addition to the constraint, we're helping our runtime decrease here by eliminating any solutions where the interplanetary spacecraft is still in a bounded orbit around the Earth. After that, we're going to step our interplanetary spacecraft to the patch point epoch and continue along there. After that, we've now stepped our interplanetary spacecraft to the patch point, so we're going to go back and do the Mars spacecraft. We initialize the spacecraft at the arrival epoch. We initialize right ascension of the ascending node, argument of periapsis and true anomaly that same way with the adjust cyclic range. However, inclination, since we initialize that with the range minus 45 to 45, we don't need to do adjust cyclic range. We just need to get the state variable value and assign it. After that, we update the second guiding constraint here, r.v. and we perform this dot product manually. This just helps with convergence to keep things simple. And then we set that constraint value. Next, we get our arrival burn components, which is just the velocity component with normal and binormal zeroed out. And we assign that to the burn and perform the burn. We add the constraint variable, our third guiding constraint here, which is the post-burn semi-major axis. That ensures that we're on a hyperbolic orbit after we've left Mars. So then we're going to step our Mars spacecraft in backward propagation to the patch point. We're going to set its central body also to the sun so that we're referring to the same coordinate system, and take the difference between the Mars spacecraft Cartesian state and the interplanetary spacecraft's Cartesian state. Then we're going to take those difference values and we'll assign the first three differences, which is the X, Y, and Z positions, and we'll assign those to the patch point constraint values, 1, 2, and 3. We'll assign the the second half of the differences, which is the Vx, Vy, and Vz components, to our mid-course correction burn. And we'll store those as a constraint for the mid-course correction burn so that we can get them later once we need it. So this doesn't really relate to any specific part of the optimization sequence, which is or the trajectory sequence, which is why none are highlighted. But we need to still minimize our objective function. So what we do here is we sum the escape burn plus the arrival burn plus the mid-course correction burn. And you'll notice something a little bit different here is we scale our objective. We divide it by 1,000. This doesn't impact the final solution, but the optimizer in general likes working with small numbers. So if you're working with something that's larger, such as the sum of several delta V values, it helps to divide it by a scale factor just to give the optimizer a nicer number to work with. The other interesting thing of note here is this if statement. So what we're doing is we're checking if the optimizer has already found a feasible solution. And if it has found a feasible solution, then we're saying, okay, go ahead and minimize. But if the optimizer has not found a feasible solution, then we're just going to tell it to minimize the number 30 divided by 1,000. So what this helps us with is sometimes the optimizer gets really close to a solution, and then it takes a guess that brings the objective function way up. And basically, it can sometimes stray away from what otherwise might be the correct solution. And so we don't want it to do that. So we're saying, look, until you get close to the actual value, we know that it should be less than 30 kilometers per second. So until the optimizer finds a value that's less than 30 kilometers per second, finds a feasible solution, then go ahead and minimize. And really, once again, it's just helping with our convergence behavior. The mission plan would work without it. It would just take longer to solve. So the next thing we're doing is we're moving into the visualization. We've finished our evaluation loop. We're going to restore the objects in process, zero out our mid-course correction burns. And then we're going to get the departure epoch, the best state variable value for the departure epoch, and the best state variable values for the different orbital elements of the Earth parking orbit. And then we'll get the best state variable values for our escape burn, assign them, and perform the burn on the interplanetary spacecraft. You'll notice the trajectory diagram here has changed a little bit, and that's because we're integrating only with one spacecraft. So everything is a forward propagation now. After that, we're going to step the interplanetary spacecraft to the patch point epoch. Once again, we know we found an optimal solution, so there's no need for that if statement to eliminate orbits that haven't escaped Earth. And then we step to the epoch and update the view window while we do it. After that, we get the values of the mid-course correction burn. So this is where that constraint comes back into play. We're using the get best constraint value for the mid-course correction burn. And that allows us to just easily pull those without having to store them out some other way. And then we'll maneuver the spacecraft using the mid-course correction burn. We step the spacecraft to Mars, to the arrival epoch, and update the view window while we do it. And then finally, once we are getting to Mars, we perform our arrival burn using the best state variable value for the velocity component and zeros for normal and binormal. And the final thing that we do here, which was not in the evaluation loop, it's just for visualization and verification purposes, is we say, okay, let's step the spacecraft for one orbital period so that we can see it in its final parking orbit around Mars. It doesn't impact the results at all, but it just gives us a nice visual and a little bit of a sanity check. So how did we do? You can see here this GIF showing the transfer from Earth to Mars. Our departure date changed just a little bit to July 26th, so shifted forward 3 days. Our arrival date also shifted forward about 3 days to February 17th. Our time of flight decreased ever so slightly to 205.7 days. And our departure delta V decreased to 3.147 kilometers per second. You'll notice our mid-course correction delta V is very small. It's only 3.2 times 10 to the negative fifth kilometers per second, which is really only about 3 centimeters per second, so fairly insignificant. But we'll talk more about that in a minute. And then our arrival delta V nearly cut in half, down to 1.884 kilometers per second, giving us a nice total of 5.03 kilometers per second. As a reminder, the Lambert solver gave a delta V of 6.4 kilometers per second, and our first optimization process gave a total delta V of 6.377. So we're already doing a lot better, and we're much closer. We're much closer to that minimum that we expected. So overall, how did we do? Our total delta V used is within the expected range of 4 to 9 kilometers per second. It's smaller than the Lambert solver. However, it's not as small as the minimum that we found using that massive trajectory browser. But those solutions don't consider parking orbits, which likely accounts for the difference. There are also some different assumptions that trajectory browser makes that weren't implemented here, which could add up the difference a little bit as well. But still, 5 kilometers per second is pretty close to a minimum that we would expect. The next thing worth noting is sensitivity is preventing the mission plan from finding a true optimum. So I alluded to this a little bit earlier, that the solution does not actually converge, rather exits out after it reaches 4,000 iterations. And this is due to the sensitivity in the transition largely from hyperbolic to elliptical orbit. So the eccentricity of our hyperbolic orbit is actually very close to 1. Some of the values were around 1.1 for eccentricity, so just bordering right on the edge of that transition, which can cause some problems because then even the smallest amount of variation somewhere in the mission plan, say at the patch point, might cause our integrated trajectory to be further off. So in other words, it might actually then be, it might not be in a hyperbolic orbit when it reaches Mars, or, it might be a little too far away to get that optimum. But this isn't really a problem that you can address by changing the parameters, because we know that an optimal solution is to be in a barely hyperbolic orbit, to have almost zero excess velocity in that hyperbolic orbit when you reach Mars. And so the optimum solution is going to be nearly impossible for the optimizer to find. That said, there are some things you can do. One possibility is, of course, just increase the max number of nominal evaluations and switch to a has not converged rather than is running. Part of why I didn't do that is it already took quite a while to run this mission plan using 4,000 iterations, and I wasn't seeing any change in the solution anyways. But if you had the time and you had the compute power, go ahead and up that number and change it. Maybe you'll get a better solution. Maybe the optimizer will get there eventually. The other approach, and this is, I think, the more reasonable approach to take, would be to use a third optimization process stacked on top of this that uses a multiple shooting approach with more patch points. So every time you break this trajectory up using more patch points, you reduce the sensitivity. And if you reduce the sensitivity, you're more likely to find an optimum solution, which is in part how we went from 6.3 kilometers per second to 5.0 kilometers per second between our first optimization process and the second one, is we broke it up into a multiple shooting approach with more patch points. And this is really easy to do in FreeFlyer. All you need to do is stack a third optimization process on this and add variables and constraints that define the additional patch points. So state variables to initialize your spacecraft, and then constraints to make sure they're lining up. Additional advantage of using this approach is more patch points with mid-course correction burns do better model a real-world transfer. Now, it's worth noting that our mid-course correction delta V was effectively 0. And of course, real trajectories do use a non-insignificant delta V at their mid-course correction points. But that's done in part to handle things like uncertainty from launch vehicle separation or variations from the actual trajectory versus the predicted trajectory. If you wanted to, and of course, the optimum case is always going to be to use, zero delta V at a mid-course correction to do all your burns at departure and arrival. But if you were looking for a solution that was better modeling the real world, dividing it up and setting it up so those mid-course correction burns were not zero, you're going to eliminate a lot of that sensitivity, and you'll likely get an optimum solution for your case where you're using non-zero delta V at your mid-course correction burns. So with all of that said, thank you so much for sticking around. I know this was a lot of text. I really want to thank Luke Schoenwetter for his help in both, building the optimization functionality along with Dave Conkey and teaching me and Julie everything we needed to know about optimization and helping me debug this mission plan as needed. I also would like to encourage people to stick around for our next talk, which is Motaz Abdelazim talking about our Meridian ground system. And then after that, we've got JP Burke talking about NASA's OSAM-1 ground system. Both of those are going to be awesome talks. I'll definitely be sticking around. But with that, let's go ahead and open it up to questions.
Thanks again for presenting. It's really pertinent now that the Mars 2020 launch just happened a little while ago. It's really cool to see that all in FreeFlyer. A question we had from the audience. Where would you get this sort of mission plan? So do we package this with FreeFlyer, or is this a special case that you've developed? How would someone outside of AI be able to get a mission plan like this?
Yeah, so this is a special case, but as I mentioned earlier, it is based off of the Earth-Mars transfer, optimal Earth-Mars transfer sample mission plan that was shipped with FreeFlyer 7.6. And basically that mission plan just considers the first optimization case. So if you're looking for, a pretty rough optimization that doesn't go into multiple shooting approach, go ahead and just run that sample mission plan. You can see how it works, get a lot of the fundamentals. If you're not totally satisfied with that and you want some more detail about multiple shooting, go ahead and email our tech support team, and we'd be happy to walk you through some of the finer points of this mission plan.
Okay, thanks. Another question, would this type of approach also work for a different celestial body that you're targeting, say the moon or maybe an asteroid?
Oh, absolutely, yeah. And so this is another great example, actually, in sample mission plans. A very similar mission plan is the optimal lunar flyby, and that does use a multiple shooting approach with several trajectory segments to optimize. It's not a transfer from Earth to the moon, although it could easily, you could easily apply the same concepts to do that. But it transfers from one Earth orbit to another Earth orbit using a flyby of the moon. These concepts are pretty generic. You can apply them really to whatever you're looking for. I just love Earth-Mars transfers, so that's why I did this.
We have another question. Can we specialize the spacecraft as dimension and weight?
Sure. So yeah, you can, change all the parameters in FreeFlyer by customizing the spacecraft, setting up different properties through the object browser. And I would encourage you to look at some of the sample mission plans in FreeFlyer for that.